Hello everyone, thank you for watching the video. Now we're going to introduce the combined loading problems as the last chapter of this course. Okay, so we have learned so far every possible stresses in the section, right? Every possible stress in the section. So let's take a look at it here, okay? I'm simply opening the notes here and I have a beam right here, this fellow right here, a beam right here, okay? This fellow here has a length of L and a section of a square section like this, okay? Simply applying forces, right? There are several outcomes I can have on it. One particular case is that I can have a directed tension, okay? That is a force directly exerted on the force on the section, so I can have the average stress, okay? And I can also have eccentricity. Okay, so I can generate a bending moment. Or A. Okay, let me clean this up. So let's use A. Okay, so that is to say I can have different stresses by a load. So let's take a look what kind of possible stresses I can have on the section due to load, right? So if you look at the step 3 here, I can have axial force generated by axial stresses. I can have shear force generate shear stress. I have a bending moment generate normal stresses. This is normal, this is normal, this is shear, so normal, shear, normal. I have a torsion generate shear stresses. Okay, so notice that my axial force generate normal stresses. Shear force, of course, generated shear stresses. Bending moment generate normal stresses. And torsion generated shear stresses. Okay, so if all this are the stress conditions I see, I can list a small table here. Okay, so forces, stresses. So I have axial, bending, and both give me normal stresses. I have shear force and torsion, and this gave me a shear stress. Okay, so this tiny table here essentially tells me that I might have a combined stress, okay, combined stress due to combined loading, All right, so we have talked about how to find the bending stresses, right? So now in a combined setting, when I look at the cross-section here, I have now x-axis and y-axis. Okay, and all these axes now has to do with the direction of stresses applied. So when I have axial forces, I simply get a normal stress in the z direction, which is in and outside the plane direction. Okay, let me redraw this axis so you can see better. Okay, so when I have a bending moment, be careful, and this is how I assign my bending moment. Why is that? You see this double arrow here? Okay, so basically if you have your 4 fingers, follow the bending direction, okay, and the thumb will give me the orientation of the bending moment. So this bending moment, we call it mx, which is the bending moment with respect to the x-axis. Correspondingly, I will have a bending moment in the y direction. Okay, that is follow my 4 fingers circling around along the bending moment. My thumb give me the y direction. This is also the right hand side rule. Okay, right hand rule. Okay, then consequently, I also can have a bending moment in the z direction, isn't it? Z direction. isn't it? So it depends on which direction my moment is, my stress is also different. Also different. For instance, if I have a moment, okay, say in the x direction, that is, this is my bending moment. If I have bending moment in the x direction, I will generate the stresses in the z direction. In the z direction, isn't it? So my normal stresses, if this is it, and then my normal stresses will go like this in tension, and like that in compression, isn't it? So when I have a bending with respect to the x direction, my axial or my normal stress is actually in the z direction. All right. But for my shear, if my shear going in the y direction, my shear stresses is actually also going to the y direction. My shear stresses is also going to the y direction. Okay. So on the other hand side, if I have y-axis bending moment, if I have a bending moment in the y-axis, okay, if I have a bending moment, say this way, sorry, this is z here, x here. I also have a normal stress in the z direction, okay, and of course this is z too. And my shear in the y direction also give me the shear in the y directions. Okay, so these are different settings when you have bending moment with respect to different axes. This can be very confusing. Okay, so let's take a look at some examples. Okay, so here's the first example. I have a hook that used to lift the force of P equal to 1.2 kilonewton. Determine the maximum tensile and compressive stress of section AA. The cross section is circular, and have a diameter of 35 millimeters. Okay, so where is AA, right? Where's AA? So this is AA right here. Okay, this is AA right here. Of course, we're not worried about this side of it. We only worry about this side of it. Okay, that's the cut right here. Okay, so first thing first, we have to do a free body diagram. So we cut right here, okay, and this is what we have seen in the free body diagram. This is the free body, okay, and for this free body, I have a force going downwards, P. I have a force that has to balance with this P going upwards, which is F. So immediately I know F equal to P, okay, F equal to P, okay, and once I understand that, I will look at the moment. I will also look at the moment. Okay, so what would be the moment generated by this force here? Right? So we know that a moment, right, equal to a pair of force, right, multiplied by the distance away from these two forces. Okay, so the moment will equal to force multiplied by distance, which equal to 65 plus 35 divided by 2. Where is the 65? This 65 basically is a distance right here. Let me label it. Distance right here is the small d, which is 65. And this half here is the gap between the outside and inside here. So this is 35 divided by 2. So that is the distance. Right, that is this. So this gives me the moment acted on the section here, on the cross section here. Okay, so now once I have axial forces F, I also have a bending moment M. I can solve for the combined stresses on this section here, Okay, so first of all, I need to find my axial stresses generated by axial forces. Okay, so I use the little table here. And I'm going to cut this little table. Okay, and drag it. Okay, drag it down here so you see it. Okay, so you see it. I need to check all the possible stresses, okay? So this is what I will do. I use my little table by sequence. I find all the stresses. First of all, I will check if I have axial stresses, right? Axial forces. So my axial force on this cross section, of course, I need to identify the section, and this is the section that I'm interested in solving, right? On this section, I have axial forces, which is F. Okay, so the normal stress, right? The normal stress generated by the axial forces is sigma equal to F divided by A equal to 1.25 megapascal. That is the normal stress. And besides, area is already calculated here. Okay, second thing I want to take a look is if I have any bending moment. So I, of course, have bending moment, which is equal to FA, right? So my bending moment here is determined here, by the way, can generate bending stress or normal stress in terms mc divided by I, where c is the distance. Okay, so how to pick the distance? So this is basically the central neutral axis. So of course, I have a negative stress, compressive, and positive stress tensile on each side. And distance c is basically half of the section here. So this is basically 35 divided by 2 equal to 17.5 millimeter. And this is what it is. Okay. So I now have bending stresses here. So this is bending. This is normal axial stresses, axial force, general stresses. So combine them together, I will arrive at the final stress state. So sigma maximum tensile would equal to the maximum tensile stress generated by bending plus a normal stress generated by axial force. And this is about here. Okay. All right. So this looks quite complicated. Okay. But we would like to establish a procedure to solve this type of problem, combined stress problem, right? So how do we do it? We first identify what type of forces exerted on the cross section here. How to do that is we have this tiny table here, okay? So we find out that we have axial forces, bending moment. So axial forces, bending moment. We don't have the shear force. We don't have torsion. Okay, so in this case, we just have to worry about the normal stresses generated by the axial force and bending moment. So we find the axial force and bending moment correspondingly, axial force, bending moment correspondingly, and calculate axial stresses, normal stress generated by axial force, calculate the normal stress generated by moment, and sum them together, and get you a final stress state. Okay, so that is how we're going to do it. Okay, all right, so next question. What if I have shear? All right, so when we have a shear, things can be very complicated. Okay, so let's take a look at this problem here. Say the joint is subject to a force of F pulling horizontally at the end of this L shape or wiggled, bent shape here. Okay, and I have a force going downwards at the tip of this bolt here too. Okay, and then the member has a rectangular cross section. It means if I cut here, I see a rectangular cross section. Okay, rectangular cross section. Okay, with a W of 50 millimeter, thickness of T to 20 millimeter. Okay, so if I do this, I will see a W. So when I cut, right? When I cut and see from top, I will have a T this way and a W this way. Okay, so this is the cross section here. Okay, and question is that need to determine the stresses, right? Determine the state of the stress at points of A and B. Okay, So have to be careful with the combined loading problem. Whenever we have combined loading problem, we need to ask you to find the stress with respect to a certain point. Okay, let me restate it. We need to ask you to find the stress at a certain point. Okay, so notice that we need to find the stress on the corner, which is B, and in the middle point of the side at A. So this is the zoom in image. This is the zoom in image. Okay, so I need to find point B, you find the stress at point A. Okay, so first thing first, I need to make a cut. This is the cut right here along A and B. Okay, once I made the cut, right? Once I made the cut, I can then examine what kind of internal forces. Step one on this cut. Okay, so a little table will go a long way. So I establish a little table here. I know that I have axial forces, Fy. I also have the moment generated, M. I also have a shear force generated, Bx. Okay, and I notice that my axial force Fy basically equal to P, the pulling down force P. Okay, and I don't have axial forces or internal axial forces generated by the horizontal force F. I do have a shear force generated by the horizontal force F, but I don't have it from P. I have a bending moment caused by the P, right? So let me erase this out so you can see better. I have a bending moment generated by P on this cross section, and the bending moment here equal to a P force multiplied distance, which is PB. Okay, and I also have, don't forget, a moment generated by F multiplied by the distance A. Okay, so this is another component, both component. All right, so after this tiny table, I summarize my axial forces here equal to 300 Newton, which is P. Shear force equal to F, 120 Newton. And moment is a combined moment by force P multiplied by distance B. And notice a minus sign. And why? Because we, in our definition here, we decide this is positive. Okay, so P goes to, sorry, this is not positive. Okay, let me erase this one out. Okay, because we now flip the orientation and name this is X, this is Y. So this would be a negative. Okay, this would be a negative. Okay, and then this would be a positive moment. So this will be a positive bending moment wise. This will be a negative. Okay, this is my sign system here for this notes. Okay, so minus PB plus FA, because FA is going in the positive direction, right? Positive, negative. Okay, and then this is the bending moment by P and by F. All right, so now I have all the axial forces here by F. Can find my normal stresses. So my A, which is the side right here, only see a normal stress by the pulling force F here. Okay, so sigma A here by the axial force. So step to find the stress due to axial force. Sigma here equal to F, total force by the area, that is the stress here. Then B, which also sees normal stress, right? So at A, B, both of them see normal stress generated by the axial forces. How about the bending moment, right? So for A, I have moment here, multiplied by distance here, divided by moment in inertia. Now, what is the distance between point A to the neutral axis? So let me flip it and let you see the cross section. So this corner here is B. A is in the middle of it and is actually right on the neutral axis. So the distance from point A to the neutral axis is actually 0. Okay, so I don't have any normal stress generated by bending moment at point A. Let me repeat, I don't have any normal stress generated by bending moment at point A. But at B, I do have a distance, and that's actually the maximum distance is half of the beam height, or the height of the section, right? Half of the beam height and height of the section. In this case, H equal to W, so W divided by 2, which is 10. And this gives me the stresses, right? And now, since the bending stress is in a negative sign, the bending moment is actually in a, let me see here. The bending moment is in a positive sign. Yes. But observe this picture, right? So observe this picture. Let me clean up this one for you, okay? My bending moment is going to be going this way. Okay, this is my bending moment, following this drawing here. So when I have bending moment going this way, apparently my B is under compression. Okay, my B is under compression when my bending moment is going this way. So naturally my B is a negative 10 megapascal. Okay, so this is a stress generated by bending moment. Okay, so remember the tiny table I mentioned here? So we go from axial forces, check the normal stress, go from the bending moment, check for the normal stress, and then see if I have any shear. And then see if I have any shear. Okay? Okay, I think I'm having some technical difficulty here. Okay, there you go. Okay, my software just freezes on me. All right, so we have checked the stress generated by axial forces. We have also checked the stress generated by bending moment. Now we're going to check the stress generated by shear forces. So what is a shear force? The shear force on AB, okay, basically will be the shear force in terms of F here. Okay, so I use the equation tau A VQ over IT. Remember? VQ over IT. But in this setting right here, let's take a look, right? So the shear force is going on the, this is a cross-sectional view. Okay, so the shear force is acting on the cross-section going this way. Immediately I realize that my A is in the corner. My A is in the corner right here. Sorry, this is not A. This is wrong actually. So my B is here. This is a typo, okay? My A is here, okay? Please correct this on your notes, okay? This is B, this is A, okay? So I immediately know that my B is in the corner here. So if I want to do the Q for B, remember we do a line cross that in perpendicular to the shear force on opposite side of it, but there's no area, isn't it? So I know that my shear stress at B would equal to 0. Okay, my shear stress at B equal to 0, but my shear stress at A have values, and the QA is an area, QA is an area, shaded area here, okay? This is QA, so I can calculate my QA correspondingly, and the T in the equation VQ over IT equal to 50 millimeter, that is across the length of it. Okay, then I can find my shear stress. Okay, shear stress at A. And you know that this is the maximum shear stress as well because it's a neutral axis. Okay, so now after all this, I can find all the stress state, and this is the diagram for all the stress state at A and B. A and B. Okay, so for a combined loading problem, we have gone through two, right? For the combined loading problem, I strongly suggest we use this tiny table here. Okay, On the left column, we check all the internal forces. Of course, you have to make the cut, crossing all the section, crossing all the points. But we need to check all the internal forces. And then find the normal and shear stress corresponding to these internal forces. Okay, so that's how we combine them. All right, I'm going to talk about one more example. Okay, so this is an example. I say concentrated loads, Px equal to 37 kips right here, Py 23 kips right here, and Pz 19 kips, center straight right here. And the beam cross-section shown as this, and B equal to 9 inches, H equal to 4 inches. So this is the cross-sectional view. And use a value of A equal to 6.4 inches. Okay. Determine normal shear stress at point K. Okay. And I label that the point K is right here. Okay. So we need to find out the stresses at point K. Okay. And also H right here. I forgot, okay? Sorry, H right here. Okay? So this seems a very complicated problem. So how to solve this? We'll solve this way, okay? First thing first, we need to do a cross-sectional cut. Okay? Now, let's do a cross-sectional cut first, okay? So this is the diagram. All right? So I have two choices. I can cut a section at H, then I can cut a section at K here. So this is very complicated. I want to ask you to read it yourself first, and we can do another video recording of this. But before I end this section, let's take a look. How are we going to make a cut? Okay, so for instance, I want to make a cut right here. At H. Okay, so when I make a cut here, I basically have a beam looks like this. I have a force going this way, force going that way. So first thing first, if I make a cut here, this is my point H, by the way. On this section right here, I need to see what type of forces I have. So I make a tiny table here, okay, internal force and cut sections. I will have X normal force, Y normal force, Z normal force. Is that right? And I can find them correspondingly. Okay, so I make a small orientation here as well. Okay, Okay, so let me zoom in. You can see it. Okay, you can see it. So at this local coordinate, okay, I have X going this way, Y going this way, and Z going this way. Okay, X, Y, Z going this way. And I call it PX, axial force, PY, and PZ. Okay, so notice that. In terms of section cut here, H, my Vn, Vx, which is the shear force, equal to Px. I have value for it. I don't have a Py, I don't have a Pz yet. Why is that? Because I'm making the cross-section cut H here. Okay, H here. Okay. And then I have a shear force of Vy in terms of Y here for K. Okay? And then I have Fz in terms of axial forces here, 19 for all of these two sections. Okay? Then I also have a bending moment Mx, because of the Px. Let me clean up this one for you. Okay, I also have a bending moment y in terms of py. Okay, but be careful, my py, bending moment py, only has effect on k, but has no effect on h. Okay, then I have torsion, Tc, but in this case I don't have any torsion, so I can omit the torsion. So after I get all my internal forces, I can calculate my corresponding stresses. Okay, calculate my corresponding stresses. And then I can get these stresses by using these equations, right? And after I get these equations, I can draw the stress element. Okay, I can draw the stress element. Now, this is a little bit long, so I have to skip it for now. But I want to go through one simple part of this problem. Is if I can find the stress at h and k, given that the bending moment the shear force are given for a particular cross section. Okay, all right. So summarizing from all these tables right here, for cross section H, I have normal force. I also have shear force in terms of x direction. Okay, I also have shear force in y direction. No, I don't have shear force in y direction. I have moment. Okay, I have moment in x direction. Do I have a moment in y direction? Yes, I have moment in y direction. Okay, and I don't have any torsion. All right, so I'm gonna make a little table here. Okay, so for cross section H, I have axial forces. Okay, I have a bending moment. I have a shear, but I have no torsion. So corresponding stress, I have normal, I have shear. So normal stress comes from axial and bending, and shear from the shear forces. Okay, so to calculate the bending or the axial forces generate normal stresses, I need to have section properties. Okay, so we already talked about axial stresses. Axial stresses right here in tension. So we're gonna omit that for now. And then I want to find a moment for section H. Okay, I have moment in y direction, which is this value here from the previous calculation of tables right here. Okay, and then for this moment, I can calculate my normal stress in z direction, use that equation. Okay, I also have a shear force right here in the x direction. So I can find my Q, okay, and this will be the Q for H, and this is Q for K. Okay, Q for H, Q for K. So I can find my Q, then I can find my shear stresses. Okay, All right. Now be careful. This is with the shear force with respect to x direction. If I have a shear force on the y direction, I have to make a cut separately. Okay, so that will be the Q. But since I don't have a point, right? So my point K is right here, and my point H is right here. They are both on the edge of it. Okay, so the shear force the shear stress due to shear force in y direction, Vy, equal to 0. Okay, Okay, all right. Okay, so I'm going to end up here because I just went through the basic concept of the combined loading. Okay, I will talk about this part problem right here in the next review, and also a exam problem from previous exam. Okay, an exam problem from previous exam. Okay, all right. So I see you